So as we continue on with our second section of this module, we're looking now at module 7.2. We're continuing looking at the analysis and design of beams for bending. Particularly, we're going to take a look at the design of prismatic beams for bending, some more shear and bending, and some non-prismatic beams as well. So objectives within this module here, we're going to examine the process for designing common types of beams, look at how the use of singularity functions instead of ordinary analytical function makes it possible to represent our shear V and our bending moment M with single mathematical expressions. And then we're also going to compare non-prismatic beams with prismatic beams. So within this module, we're going to go over some of the key theory and concepts, talk about some of the governing equations, some practical applications, and go through a couple different problems that we're going to solve together. So as we get into module 7.2, I want to go through a couple example problems utilizing the equations and theory that we saw back in module 7.1 that'll roll into module 7.2 as well. So first example problem I want to take a look at here is sample problem 5.2. Now in this problem here, they give us most of the information in this diagram up top here. So we can see in this diagram right here, what we have is we have a structure shown to be constructed of, and they tell us the type of steel I-beam that we have right here. So we have a rolled steel beam with a W10 by 112 rolled steel beam. So that's going to be important. And with our textbook here, we can actually go into the back into Appendix E and look this up. This is also something that you could look up online from the manufacturers and a lot of different material sheets as well for this W10 standard 112 rolled steel beam. So now we can see this beam goes from A to B. We can see we have a fixed support over here at B. You can see we got a distributed load right here from A to C of 3 kips per feet right here, and it's 8 feet long. Then you can see there's a 3-foot gap between C and D, where D we have this situation going here where we have a load of 10 kips applied at E, where E is 2 feet long and goes over this beam right here at D right there. Then 3 feet away from the end of E, we have our B, which is our fixed supporter. So there's a lot going on within this here. So what are they asking us to solve for? Well, they want us to solve for 2 different things in this problem right here. In part A, they want us to draw the shear and bending moment diagrams for the beam and the given loading. So this is similar to what we've done in some of the previous problems in the module 7.1. And then they also want us to determine the maximum normal stress in sections just to the right and the left of point D. So right there and right there, we'll be taking some sections right there. So now we have an idea of what they gave us in the problem. They have all the dimensions up here in the diagram right there. They tell us what type of beam we're dealing with, and we know we're looking for shear and bending moment diagrams of the beam and the given loading, and then we need to determine the normal stress in sections right there and right there. So with all this information that we have in the given diagram here, along with all the information in our given problem statement here, the next steps we're solving this out by hand were to create that setup page with everything, a simplified version of this diagram, all of our givens clearly written out with the variable name, numeric value, units, and how it relates back to our problem. And then below that, everything they're asking us to find. So these 2 different parts of things they're asking us to find, that shear and bending moment diagram, as well as the maximum normal stress we listed under our finds. And then we'd also list out any assumptions that we're going to make for this problem. So after we have that setup page, we can read through that and determine what is our procedure for analysis. So our procedure for analysis is listed over here under solution. So the first thing that we're going to want to do is replace this 10 kip load with an equivalent force couple system at D. So if we go over here at D, we can see this is pretty complicated going on here. There's our 10 kip load right there. This is applied to this 2-foot member right here, which then comes down here onto D. So we want to go ahead and replace that 10 kip load with what the equivalent force couple system is at D. The other thing that we want to do within this step here is to find the reactions at B, our fixed location over here, considering the beam as a rigid body. So that's the first step that we're going to do in our procedure for analysis. Then from there, we can move on to the next section within this. which is where it's asking us to section the beam at points near the support and load application points. So we can go through all of those right there and figure out where we can section that there. Then after we found those, we can apply the equilibrium analysis at the resulting free bodies to determine the internal shear forces and bending couples. This is the same type of thing we did in the previous problem there. We go find all those points, go ahead and create our sections at that point, and then each of those sections right there is going to have an equivalent free body diagram. Deal with each of those free body diagrams separately, write out all of our equilibrium equations for each one of those, and from that we can solve the number of equations, number of unknowns, in order to get these internal shear forces and our bending moments and bending couples. Then last, to get down to our part D or part B down here, where we're determining our maximum normal stress. This is where we're going to apply that elastic flexure formulas to determine the maximum normal stress to the left and the right of point D. So this time here, again, we're sectioning it there and there at the left and the right of point D. So as we jump into our solution here, we'll go through that procedure for analysis. And first off, let's take a look at that very first step and even just the first part of that first step. So the first part of the first step is right here. This tells us that we want to replace that 10 kip load with an equivalent force couple system at point D. So this is the area that we're looking at right here. So what I want to do is redraw this on its own and treat it as a separate problem, a separate part of this whole assembly right there, so we can get that equivalent force couple system at this point D. So I look up here, I've got this 10 kips right here. I know it's 2 feet right there. So I draw this out. There's my 10 kips right there. There's my 2 feet distance over here to where D is down there. So this load's acting at E at the top right here, 2 feet away. So let's just say, okay, now I'm going to have an equivalent force down there and moment down here. And this is what I'm looking for, my F sub D and my M sub D down there. So let's do our equilibrium analysis right here. So we have summation of forces in the y direction. Well, what are our forces acting in the y direction? Well, I have this 10 kips, and if I do this as my standard XY coordinate system right here, where X is positive to the right, and my y is positive up here like this, then I have a negative 10 kips, and I have a minus FD right there. So this is equal to 0, so I can move this over to the other side right there, and I say that negative 10 kips is equal to FD, or FD is equal to negative 10 kips. Now I want to do the same thing for my summation of moments about this point down here at D. So summation of moments about that point down there is equal to, well, I've got this force right here, times this distance right here. And this is going clockwise, so that's negative. So that's a negative 10 kip times my 2 feet right there. And then I also have this reactionary force down here, or moment down here, my M sub D right there, the equivalent. There's my equivalent couple of reaction down there. So this is my M sub D down there. This is going to be negative MD there. So I can say that negative 10 kips times 2 feet is 20 kip feet. Negative 20 kip feet is equal to, move that to the other side, MD. So MD is equal to a negative 20 kips times feet right there, which is then going clockwise, so that's true that that's negative. So from this here, now I have that equivalent force couple system down at D, and I can look at the second part of this problem right here, where our procedure for analysis asks us to find the reactions at B by considering the beam as a rigid body. So that's what I want to do next. I want to take this as an entire beam. So I'm considering the beam as a rigid body all the way from A to B right there, and I want to find the reactions at B. So now what I can do is I can take a look and draw out my entire free body diagram for this beam all together. So that's what I do there. I say, okay, first off, I already know what's going on here. I've just figured this out. So this is 10 kips right there, acting right at point D, going down like this, and I have my moment M sub D right there that I have a value for as well. So I can put that in there. I still know I'm going to have my reactionary force here at the fixed end of the beam right here. I have my R sub B right there, and I'm going to have some internal moment right there, my M sub B, my reactionary moment right there. And then I know these distances from there to there. That is 5 feet, because that's the 3 feet plus the 2 feet to get to D. And then at C, what I can say is from A to C, I have this distributed load. So my distributed load is 8 feet long, and it's 3 kips per feet. So 3 kips per feet times 8 feet is 24 kips. Right there, our feet cancel out, so I'm left with 24 kips, and that's at the dead center of this. So this dead center of that would be 4 feet from the end there. So there's 4 feet from the end there, and then it'd be another 4 feet over here. So 4 plus 3 would give me 7 feet to get from D to where my load is right there, and then 4 feet to the end over here. So now I have a nice free body diagram for considering the beam as a whole rigid body right there. So let's do again summation of forces, our equilibrium analysis right here. So say, let's take a look again and just do our standard XY coordinate system, X positive this way, Y positive this way right there. So our moment is going to be positive. We do our right hand rule. Our moment's positive counterclockwise and negative clockwise. So with that there, now I can say, okay, summation of summation of force in the y direction is equal to 0. So what are this force in the y direction? Well, I have this r sub b right here, this reactionary force I need to find, which is what they want me to do. My reaction's at b. And I also have a negative 10 kip there and a negative 24 kip right there. So I can say r sub b positive, going up in my positive y direction, minus 10 kip minus 24 kip is equal to 0. And then I can do the same thing for my moment equation down here, summation of moments about the end of this beam. Let's just do it right about the end of here. Well, I'm going to have right here this 10 times 5, and that's going to be positive. That's going counterclockwise. And then I'm going to have my 24 by 12, and that's going to be the 7 feet plus 5 feet equals 12. So 24 times 12 is right there. And then I'm going to have a minus 20 kip right here. So this is my minus 20 kip, my m sub d. This is my m sub d right there, is that minus 20 kip right there. And then we have that force over here, which I'm going to have my minus m sub b right there. So this is equal to 0 there. So now the only unknown in this is my r sub b in my force equation and my m sub b in my moment equation. So 2 equations, 2 unknowns. Now I can solve those out. So that's exactly what I do next. Still have my free body diagram up here for my beam as a whole right there. And below that, I now have my summation of forces. So again, summation of forces in my y direction, r sub b minus 10 kip minus 24 kip is equal to 0. So r sub b minus 10 minus 24 is minus 34. Move that to the other side, so my r sub b is equal to 34 kip. Now I do the same thing for my moments. I have my 10 kip times 5 feet plus my 24 kip times 12 feet minus 20 kip right there minus m sub b. Let's move the m sub b to the other side. This is equal to my m sub b. My 10 times 5 is 50. My 24 times 12 is 288. And we have negative 20 we can bring down there. So let's combine these all together. 50 plus 288 minus 20. So m sub b is going to be equal to 318 kip feet. So now I've completed the first part of this procedure for analysis in my solution right here. I've replaced that 10 kip load with the equivalent force couple system at D, so we can see that right over here. And I've also found my reactions at B, so we can see that right over here. So I draw that all out in the top of this diagram here, and I begin the next step where I need to section the beam and apply my equilibrium analysis on the resulting free bodies. So we need to create the free bodies for each of those as well. Now again, if I was doing this out by hand, I'd want to do each of these separately. Now there's 3 different areas I want to take these sections. So I see section 1, section 2, and section 3. Now where I want to take these is the first one, section 1. I want it to be somewhere in between A and C, where the distributed load is. I want to do the second one somewhere between C and D after the distributed load, but before we get to that point D, we have the equivalent couple and force right there, and then somewhere between D and B, where B is the end where it's fixed right there. So I can say, okay, I'm doing it from A to C, C to D, and D to B right there. Now where it lies in that is going to be some distance x. So if I come over here some distance x over like this right here, then I say, okay, this is going to be, when I'm in between A and C, this is going to be my free body diagram for that section there. So however far over I go, I can put this down. This is going to be 3 times whatever that distance is, because it's 3 kips per feet. So 3 times whatever this x is in feet right there is going to be this load acting down there. And this distance right here is going to be in the center of it right there. So whatever that distance is divided by 2. So that's why we have an x over 2 right there. And then I'm going to have, on the other side of my free body diagram here, there's my force V, my shear force there, and my moment right there, M, like that. So with this one here, let's take that free body diagram right here. Now that we've drawn that out for any x distance in between A and C right there. And what we can do is let's just say, okay, let's do out our equilibrium equations right now from A to C. So what are my forces acting in my y direction? Summation of force in the y direction is 0. Well, my forces are, we're going to have this negative 3x right there going down right there for my distributed load. And I'm also going to have my negative V is equal to that right there, is equal to 0. So I can solve that, put my V over on the other side, and V is equal to negative 3x kips. So that means that regardless of what my x is, I can put an x in value right there between A and C, and this is what my V is going to be at that area right there. Now, let's take a look now at our moments down here. And so let's just say the summation of moments right here for that first section right there is equal to 0. So what are our moments acting right there? Well, we have this 3x times this distance away from the end over here right there. So that's 3x times 1/2 right there, and that's going counterclockwise. So that's going to be positive. And then I also have this m moment right here. So this is going to be plus m is equal to 0. So I have 3x plus 1/2 x is equal, plus m is equal to 0. So m is going to be, when I move to the other side like that, negative 1/2 x squared kip times feet. And again, this is all dependent upon x. So this could be for any value of x. So this is very useful if we want to step this along the way and figure out what our shear shear and our moments are at any distance between A and C, any distance from A in that range right there, we can do this here. We can plug this into MATLAB. We could do some other type of Python or some type of numerical analysis method right there, even in Excel. And we could automate this to plug in different values for X on very, very small increments to find out what our shear and our moment are that whole way along that. So this is a way that we can kind of lead into numerical analysis of this here as we get an infinite number of these sections that we're interested in along the way. So that's from A to C. Now we can do the same thing from C to D. So from C to D, if we want to do that same thing right there, we're going to draw this out to some distance over here. This is part 2 right here, or section 2 right there. So now we can, let's erase some of this other stuff here. Now if we look at this from C to D, what we have here now is this goes out a little bit further now, and it goes past that point C. So we have this entire distributed load right here, which is going to be this 3 kips times the total distance of 8 feet. So that's why we have this 24 kips right there, and that is distance of X minus 4. So we know that this distance from there to there is 4, and this distance from there to there to 4. So this distance from right here is added into that right there. So whatever distance out in the X direction we are, we have this relationship now here for how far this force is away from where we are at the end section right here, which is this distance X right there. So X minus that 4 is that distance between now this load and this end point right here. We're going to have our equivalent shear force and moment right there at the end of that. So with this here, now we can do our equilibrium analysis from C to D. So that's what we look at there, and we say, okay, now we're looking at this diagram here. So let's clear this off for a second for us. And if we look at this diagram here, now we can say what are our forces acting in our y direction. So summation force in the y direction is equal to 0. Well, we have a negative 24 with our coordinate system, and we have a negative v equals 0. So negative 24 minus v is equal to 0. Move the v to the other side. V is equal to negative 24 kips. Now we can do the same thing about the moments about this end over here. So the second set of moments right here, m is equal to 0. Summation of all the moments is equal to 0. So what causes the moment? Well, we have this 24 kip times x minus 4, and that's going counterclockwise, so that's positive, plus this m right here. This is equal to 0. So m is equal to 96 minus 24x when we combine those two right there. And this is going to be in kip feet right there. So again, this is going to be dependent upon our x value right there. So we can plug that in. And with any x value, regardless of how far we go, again, between C and D, this is what our moment is going to be there. What you can notice is, regardless of that x distance right there, our force is still going to be negative 24 kips because of that distributed load over there. So now what we can do from here is we can take a look at the last section from B to D. So let's clear this off for a second, go down and look at our next free body diagram down below. So if we come down here below to our last free body diagram right here, again, now we're going between B and D right here at 3 right here for this section right here. So we can take a look at this guy here and do the same thing that we did before. Say, okay, well, now we've got this equivalent load right here. When we break this down again, 3 kips times 8 feet is 24 kips. We know that distance right there. And if this is now our x distance all the way over to here, then we can figure out from there, well, this is going to be our x minus 4 distance between the end of our beam right there and that load from our distributed load right there. Then we're also going to have in this information here. Now we have this load right here, negative 24 going down there, or sorry, negative 10 going down here, and then we have a 20 kip going right there. And at the end, we have our equivalent V and our equivalent M. So we would do the same thing. We skipped a step right here, but we could do our summation of forces in our y direction, and we find our summation of forces in the y direction. Well, we have a negative 24, and we have a negative 10 right there is equal to 0. So negative 24 minus negative 10, we can find that our V then is equal to negative 34 kips right there by doing our equilibrium equations out just like that. And then we do the same thing for our moments right there. We can say we're going to have this negative 24 kip, or sorry, positive 24 times x minus 4 right there, and that's going to be going counterclockwise, so that's positive, minus 10 kips because that is going this way, and we have an m over here that's going, again, counterclockwise right there. So we end up with the relationship when we do our summation of moments, similar to we've done it up here before. We can find out now this m is equal to 226 minus 34x kip feet. So now that we have that information that's dependent upon what our x values is, what we can do is create our shear and moment diagrams based upon the x information of A, C, B, B, and D. So we take the information that we found before. We found that, okay, our shear force between A and C is going to be equal to -3 times x in kips. Our moment from A to C is going to be -1.5x squared in kip feet right there. Well, at A, x is equal to 0, so 3 times 0 is 0. And our moment as well is going to be 0 right there, so that's equal to 0. So we can see both our shear and our moment diagrams at point A are 0. Now we're going to do the same thing for our point C right here. For point C, our x is equal to 8 feet right there. So if we plug in 8 right there, then we have a -24 for our point right there. So we can draw a line right there, from there to there, from 0 to -24 kips right there. So that's our shear diagram right there. And then we can plug in an 8 right here now for this value right here for our moment down there. So I draw our moment, 8 squared times a -1.5, that'll give us a -96 kip feet right there. So this goes like this, and then this curves up like this right here because it's a squared term, it's not linear right there. So that's a squared function right there, so we can plug that in right there. Now, this is something that I'm talking about right now, is drawing this by hand. You could also take and go with incremental values. Maybe you could go by 1. Right there between 1 and 8, do it every foot, do it every half foot, do it every inch, and you could plug this into MATLAB, you could plug this into Excel or anything else and plot those out and draw that curve from there to there by following these two functions. So you can find that this is linear, -3x, and this is going to be exponential right there to the squared function right there. And you could get the shape of that curve a lot more accurately than just drawing it and saying, oh, it's a squared term. So you could plug this in and actually graph this out in Excel, MATLAB, or anything like that. So that's something that I would suggest getting comfortable with as we get into some of these functions and talk about how we can transition into numerical analysis with this. So now we want to do the same thing from C to D right there. So we look at this here. Well, our shear diagram we're going to have here, our shear is going to remain constant at -24 kips the whole way. So right there, from x is equal to 8 to x is equal to 11, this stays right at -24 kips that entire time. And then we can go down here to our moment diagram right here. So if we're continuing on from there to there, we can say as well, this is going to follow 96 minus 24x right there. So we can plug in that relationship there. Now we know at x is equal to 11, we're at D right there. We can plug that in and solve for this value here of -168 kip feet right there. So this is the relationship we're going to follow along there based on this function. And again, you can plot this in MATLAB and change your x values smaller, smaller, smaller to get more accurate value for that there. Then the next thing we're going to do is we're going to jump from B to D right here. So I'm going to erase this just for a second so we can see what's going on right here. And now if we go to from B to D right here, at B at the very end of this up here, we can see we have a value over here of x is equal to 16 feet right there. So what we can tell from that is that it's going to change a couple things. One, we're going to do these little step functions on both our shear and our moment diagram. So even though our shear was dead on at 24, up until that point 11 right there, from C to D, it's going to jump directly up here to -34 kips. That's why we have this steep step right there on our shear diagram as it jumps right up from -24 kips to -34 kips. So it does a 10-step jump right there, 10 kip jump right there like that, and then it remains constant at 34 kips all the way until we get to x equal 16. So from x equal 11 to x equal 16, V remains at -34 kips. Now our moment follows this relationship down here, -226 minus 34k. So we see that value right there linearly increasing like that as well. We see that little step down as it goes from -168 back here between C and D. As soon as we get to D and go from D to B, it jumps up to now this value of, or drops down to this value of -148 kip feet right there. And because that's we start right there, we plug into this relationship right here to jump it up like that. And then it goes all the way up until we plug in x equals 16 at the top right here of -318 kip feet right there. So this is why it's important to really take a look at these. And it might even change the shape even more if we were to go ahead and plug in these, like I said, to a numerical solver and slowly decrease, refine that size right there of the x values right there down to every foot, every half a foot, every inch, so on and so forth, so we can accurately get the shape of these shear and moment diagrams that we're creating here. But this is how we get it from the relationships that we found relative to x in all of these guys right here as we create our shear and moment diagrams. So now we recall the next part and the last part of this problem they asked us to solve for was determine the maximum normal stress to the left and to the right of point D right here. So we want to do this on the left and the right of point D right there in order to get that maximum normal stress right there. So we can go back to Appendix E in our textbook. And when we go back to Appendix E in our textbook right there, what we see is we can look it up for what they gave us in the problem statement, W10 by 112 rolled steel, and we can get our value for this here. So let's go right now and take a look at Appendix E. So here is Appendix E right here. We can see this is the properties of rolled steel shapes. This is in the back of your textbook right there. So you can see Appendix E. So these are W shapes, these wide flange shapes right there. So that's what our W stands for right there. We can see a general shape of this right here. So maybe if they hadn't told us this, they may have given us all these dimensions, which we could come down here and plug these in and figure out which one we had. But we want to look over here as our S value right there in inches cubed, as long as the XX axis right here. And we can see we come down here for this, follow this one over like this, follow this one over right here, and we get a value of 126 inches cubed. So now we can go back to that equation and plug in. So now that we obtained that value from Appendix E in the back of our textbook for our W10, 1012 rolled steel for that I-beam shape right there of 126 inches cubed, about that XX axis, what we want to do now is take a look down here at our moment diagrams and calculate out what our moment is. We want to convert it now into kip inches rather than kip feet for the next section of our problem to calculate that normal stress right there. So I'm going to do this ahead of time. So from the left of D right here, we can see this have this negative 168 kip feet right there. So that's a negative 168 right there. And we're going to want the absolute value when we plug into our governing equation right there. So the absolute value of that is 168. Convert it to inches, multiplied by our 12 right there. So this is 216 kip inches. Same thing to the right of D. Now we're at negative 148 kip feet right there. Absolute value of that, 148 times 12, is our 1776 kip inches right there. So then we come back to our governing equation right here. So our normal stress, our max normal stress, is equal to the absolute value of that M value right there to the left of D right there, our maximum moment value right there, divided by that 126 inches cubed for our S value that we looked up from Appendix E. So 216 divided by 126 is kip inches over inches squared right there. We ended up with over inches cubed right there. So the inches cancel with with one of the inches on the bottom. You're left with a squared term on the bottom right there, which is exactly what we expect right there of KSI. So our normal max stress right there is 16 KSI. To the right of D, it's the same thing, but right now we're using the value when we convert it to negative 148 into inches rather than feet right there. So that's 1776 divided by 126 inches cubed there. Inches can cancel like that, leave you with an inches squared right there. And now this ends up being, for to the right of D right there, a max normal stress of 14.1 KSI. So now I want to take a little bit of time to discuss the design of prismatic beams for bending right here. So in this section right here, we're going to take a look and examine the process for designing some common types of beams right here. So this might include some timber beams of rectangular cross-sectional areas. It may be rolled steel beams of various cross-sections that we just took a look at in the previous example problem right there, where we're able to go to the back or appendix and get some information from that if they tell us exactly what type it is. So this is something, again, if we're tying this into talking about the design, this course is going to lead into some future design courses for you, maybe your seed project, maybe onto research for grad school or a company. So as you go forward, this design aspect of this becomes more and more important. So you'll notice as you proceed forward in your curriculum here, less and less information may be handed to you and given to you or spoon-fed to you for these problems, and you may need to go to outside resources, whether it's the appendix in the back of your book, the manufacturer, materials tables and charts, things like that, in order to get more information. And all the time they might not tell you you're exactly using this. It may be up to you. It may be part of your design parameters right there where you're saying, do I use wood? Do I use steel? Do I use aluminum? Do I use this shape? Do I use that shape? Or that's up to you as the design engineer to pick that information out. So that's something as we move forward to consider. For this course here, most of the information given to you within the problem statement, you can probably go and get what you need from it further from the appendix in the back of the book. But also consider that the appendix doesn't cover everything, and you may need to look to outside sources as well. Another thing to consider when we're talking about the design of these beams right here is that a proper procedure should lead to the most economical design right here. So this could be cost, weight, it could even be ecological effects as well that could tie back into it. So what this is kind of leading into here is we're talking about here that among beams of the same type of material, so the same type of beam and the same material, so the shape of material is already specified within that there, and other things being equal, the beam with the smallest weight per unit length and thus the smallest cross-sectional area should be selected right there. So typically the less weight, the less dense, the less material you're using right there, the cheaper it's going to be. But also you want to do it within your design parameters though, so you can find that happy medium. You don't want to go such a small cross-sectional area just to save some weight and money and then find out, well, that's not going to have the stress I need. It's not going to be able to withstand the stress or the forces or the loads or whatever it is that you're applying to it. And again, as we're stepping forward and thinking in the future here about designing of these right here, it's not just the max load that's sitting on it right there. It's also with a safety factor. Are you talking about static loading? Are you talking about dynamic loading? There's a lot more that goes in as we get more and more involved with this design process here. So these are things I want you to start considering and start thinking about as you're doing these calculations and formulas for these problems. So as we continue on with our discussion of prismatic beams for bending and talking about the design aspect of this, what we want to do is come up with a procedure for analysis for this design process right here. So first thing we want to do is take a look at step one. Step one we want to do is we want to first determine the value of our sigma sub all right there, where this is sigma sub ALL is the allowable stress for the material used. So if we want to determine this for the material selected, this is a material maybe from a table or from some of your design specifications. You may be looking this up from the actual manufacturer. You may be looking up from MATLAB. This may be from the appendix in the back of your book right there. For whatever the material is that we selected, this is something we might be able to possibly look up. Now we can also calculate this value or compute this by dividing our ultimate strength right here of the material right there, our sigma sum u, by the appropriate factor of safety. So this is where we talked about that safety factor right there. And this is something that's important to start considering from the very beginning of our design process. This shouldn't be an afterthought at the end. We need to anticipate that people will use these products, use our design outside of its intended purposes. And what we think might be a good max load that we should design to, somebody else may double that, put 2 people on it, drop something on it, use it for an unintended purpose right there. So that's why we need to have this factor of safety in there as well. So that's something that goes into the computation of this allowable stress for the material there. So this is going to help us pick which material that is based upon that factor of safety. So now, assuming that this value for our sigma all for this allowable stress is going to be the same in tension and in compression. If that assumption holds true, then we can proceed with these following steps here. So in step 2, what we're going to do here is we're going to draw out our shear and bending moment diagrams corresponding to the specified loading conditions, and then from there determine the maximum absolute value, our M sub max right there, our absolute value of our max moment of the bending moment of our beam right there. So this is something we saw in a couple of the previous problems, example problems we went through, and find out how to calculate these right there as well. So again, this really helps us from our free body diagrams and our equations of equilibrium equations as well. That's how we can calculate this absolute value of max right there for our bending moment in the beam. So we have seen this in a couple of different example problems. So moving on to step 3, from step 3 what we want to do is determine from our equation 5.9, which we can see down here is our equation 5.9 from our textbook right there, we want to find the minimum allowable value, this S min of the section modulus of the beam. So that is right there where we can use that bending moment, that max moment right there, that absolute value, divided by, there we go, there's our allowable stress right there, our sigma sub AL. So we can divide that right there in order to get our S min right there. Now let's consider something else. We're in step 4. Let's just take, for example, a timber beam right here. So the depth H of the beam and its width B of the beam, or the ratio of HB, are characterizing the shape of its cross section. Now this probably will have been specified, but there are cases where they don't specify this. And the problem right there that you might be something in the design process, especially as we move forward with future courses, as you move along with your curriculum right here, there's going to be less and less information handed to you in the problem statement. This is stuff that you need to actually come up with in the design process for that there. So this is a case right here. Well, if we don't know, if these dimensions are unknown, we can find those by utilizing the relationship shown in equation 4.19 in our textbook right there, where we can say, okay, we can calculate out, we can back calculate our B and our H so that we satisfy this relationship right here that comes from equation 4.19, or the full equation right there. So if we can figure out, okay, if our S right there is going to be greater than or equal to that S min, which we calculated from 5.9, then from that there we can at least calculate our BH squared value right there, which again, this right here could also be our area right there, base times height right there, times our height again right there. So if we can find that value right there for our S value right there and make sure that this calculated value from this equation here is greater than or equal to our S min, then we can know that, okay, those are good values for our B and our H, or the dimensions in this case here for our height and width of our timber beam. So another thing we want to consider when we're talking about the design of these beams is that our largest normal stress is going to be found at the surface where the max bending moment occurs right there. So this relates back to these two equations in your textbook right now, 5.1a and 5.3a right there, where we have this maximum normal stress is equal to, there's again what we talked about in that procedure for analysis right there for the step and for the design right there, the absolute value of our max moment right there times c, where c is that distance out to the outer surface of the beam that you're looking at right there, divided by your value for I. Now the C over I relationship can be replaced by this value right here, which is the inverse of that right there, which is equation 5.3a in your textbook right there. Now, another thing to consider here is we're talking about these safety factors and a safe design. So this requires that the maximum normal stress be less than the allowable stress for the material used. So that's something to look at when you're picking out your material types right there, that this needs to be less than the allowable stress. You got to look up that allowable stress from those tables, those charts right there, and make sure that your max normal stress is going to be less than that. So this criteria can lead to the determination of the minimum acceptable section modulus right there. So we can kind of back that out from these equations back up here. So if sigma max needs to be less than or equal to the sigma all right there, then we can say that our S min right there is equal to, again, that absolute value of our max moment all divided by that sigma of all right there. So this relates back to equation 5.9 in your textbook. So again, back to the design criteria process, things to consider, and this is just a small fraction of things to consider. As you get into future courses, we'll go further and further with this, but among the beam selection choices, which do have an acceptable section modulus, the one with the smallest weight per unit length or cross-sectional area will be the least expensive, typically, if it's the same material right there, and be the best choice right there. So again, I just don't want to lead you in the false direction here. It's not just the weight and cost that are important right here. There may be other criteria. There may be environmental criteria that are very important, and maybe that will actually end up changing the cost because your waste products are going to cost you more money. And the machinability of that part right there. So even if the material, the raw material is a little bit less expensive, you know, if it's a stainless steel versus something else, is it harder to machine? Is it going to be in a corrosive environment? So there's other materials you can't choose out of that. So it's not all fine detail right here where it's just like, this is cut and dry, this is what it is right there. There are exceptions and a lot of different factors that we do need to consider in this design process. And again, we'll get into more and more of those as you get further along in this course and get into some of your other design courses, specifically ME 171 Design of Elements course right there. We'll really take all these factors in and talk about the entire design process as a whole. So this right here, we're talking about, you know, choosing the one with the smallest weight, you know, per unit length or cross-sectional area will be the least expensive. Potentially could be the least expensive, but depending on your machining and your wastes. And is it the best choice? Maybe, depending on the specifications at the beginning of the problem. So this is a really oversimplified case with some large assumptions, and I don't want to mislead you with that. So now let's go through another example problem. Let's consider sample problem 5.8. So in this problem here, we have this given diagram up here. So we have this simply supported beam right there. We have our supported A. We have a supported D over here. We can see we have an external load right here, point load of 50 kilonewtons. And we have this distributed load from A to B of 20 kilonewtons. And we know that the distance between A and B is 3 meters. From B to C is 1 meter. And from C to D is 1 meter as well. So within this here, we have a 5 meter long, so that's the total length, 3 plus 1 plus 1, simply supported beam. So we can see it's simply supported at A and D right there. This is all beam AD. And this is to carry the distributed load we see from A to B right there and the concentrated loads that we see over here, that 50 kilonewton load right there. Now, knowing that the allowable normal stress for the grade of steel to be used is 160 MPa. So that's our sigma sub ALL right there, is given to us now as a value of 160 MPa. This, from there, we want to select the wide flange shape that we should be using. So this is kind of the reverse of some of the problems we've seen before. So rather than this telling us what the beam is, this is more of a design problem. So our criteria, our specifications, the information coming from our client, our funding agency, the research project, whatever it is telling us, hey, this is the maximum allowable stress that we can have for the situation here. These are the types of loads you're going to have. Now you let us know as a design engineer what we should use, what wide flange shape we should use to meet all of these specifications. So within this here, what we want to do next is first create our setup page, write all this information out, all this given information under the givens, all of the things they're asking us to solve for under the finds, and the assumptions we're going to make. Once we have that, then what we want to do is begin our procedure for analysis right here. So for our procedure for analysis for our solution, What I want to do first is consider the entire beam as a free body diagram. So we're going to write this all out, draw this out, simplify down our initial diagram over here, create a free body diagram, and with that free body diagram, do our equilibrium equations and determine our reactions at A and D. So we want to find out what our reactions are at A and D. So then once we've done that, next we want to develop a shear diagram for the beam and load distribution. So that's our shear diagram that we're going to need to come up with there. So we've done one of these before. They're not asking for a moment diagram yet, but right now first part is a shear. Now from the diagram, determine the maximum bending moment. So we do still need to find the maximum bending moment. They've only asked for the shear diagram, but we do need to find the maximum bending moment as well for this right here. Next, we're going to find and determine the minimum acceptable beam section modulus right there. So this is a little bit different than we've done before, a different order right there. So I want to think about this. How do we determine that minimum acceptable beam section modulus? And from that, choose the best standard section that meets the criteria right there. And that's what they asked us to do at the end there. So this is our procedure for analysis, and little steps, little solutions we're going to find along the way to get down to what they asked for in the end. So the first thing I want to do is the beginning part of this there, where we consider the entire beam as a free body diagram and determine the reactions at A and D. So I've drawn this out just within PowerPoint here, a nice simple one, and normally this would be a hand solution, but that's a side note right here. For your homeworks and exam problems, if this is easier for you, it's easier to draw this out in a different program, in Paint, Illustrator, or in my case right here, just in PowerPoint, and create your free body diagram that way. By all means, please do that. If this helps keep you organized, it's a great way. Once you have one of these, you can save them and reuse them and move things around for other problems as well. So it's a good thing to invest the time into. So for our free body diagram right here, here's our beam AD right there. So we can see, well, we have our reactionary forces here at A, we have a reactionary force here at D. We have the distributed load that's been condensed down now in the halfway mark. So it's in between that 3 meters total. So we've distributed this down. So this is 60 kilonewtons at a distance of 1.5 meters away from our point A right there. So that's something that we were able to find by looking at that distributed load and paying attention to what it was given to us as and where the halfway point is. So that's now how we created that 60 kilonewtons right there. Then we see between that 60 kilonewton load from our distributed load right there over to our other load right here, our point load over here, 50 kilonewtons right there. That's 2.5 meters, and that's 1 meter right there from the end over here where we have our reaction force D right there. So I'm going to go with a standard coordinate system right here. Standard X to the right positive, Y up positive. Now the first thing I'm going to take a look at here is what are my moments about the end of the beam over here. So this is going to be an equilibrium, so this is going to be equal to 0. So what creates a moment about this end right here? Well, I have this force right here, my reactionary force D, times the whole distance here. So 1.5 plus 2.5 plus 1 right there is a total of 5 meters times D. That's going counterclockwise right there. So that's the positive direction, counterclockwise, according to my right-hand rule. If I take my fingers, curl them from X up to Y right there, that's going to be a positive coming out of the board right there. So that's a positive moment right there. Then I also have my 60 kilonewton load and my 1.5 meters away right here. So this right here is going to be going clockwise. So that's a negative moment right there, 60 times that perpendicular distance of 1.5. Then I have my 50 right here times its distance right here, 4 meters, 1.5 plus 2.5. And again, that's going to be negative because it's going clockwise. So 50 kilonewtons times 4 meters right there. You can multiply those all together. This is one equation, one unknown for the situation here, so I can solve for D. When I do that, I find that D is 58 kilonewtons, and it's going up in a positive Y direction. I put this little arrow here. This is another way to double check your sign convention. If you don't want to reference back, okay, positive means up, negative means down, you can always put a little arrow next to it too, just to double check and make sure you've got your sign convention right. So then I want to say, what are my summation of my forces in my Y direction right here? Well, what are all my forces? In equilibrium, this is going to be equal to 0. Well, I have my AY right there. And I also have my D, which I've just solved for from the moments right there. So this right here is D of 58 kilonewtons right there, minus 60 kilonewtons from my distributed load, minus 50 kilonewtons here from this point load that was given to me in the problem statement. So my only unknown now that I've plugged in for my D right there is my A sub Y. So my A sub Y is going to be acting up in the positive Y direction. And that, when I solve that out and solve for the one unknown in this equation, is 52 kilonewtons. So next thing we want to do is section this member out at individual parts. So we'll section it at B, we'll section it at C, and we'll section it at D. We'll do out the free body diagrams at each of those, and then we'll do our equilibrium equations in order to find our shear values that we're going to use to create our shear diagram right there. So if we need to calculate the shear forces right here, the first thing we're going to do is we'll just take a look at the first section right here. We'll section this off right at point B right there. So if we section it at point B, we come down here, we cut right through this guy, point B right there, and we end up with this free body diagram right here. So with the free body diagram, we can go up to the full free body diagram that I redrew right here. And what we can see here is like, well, we got our supports over here is our A sub y. Here is our 60 kilonewton load right there. And there is our shear VB and our moment MB right there. Really not concerned about moments. We're just looking at our shears right now. Well, what we're going to do now is we're going to say, okay, let's pick a standard coordinate system. So we're just going to go with the standard XY, X positive to the right, Y positive going up right here. So now we take a look at this free body diagram down here for this first section at B. We say, okay, what are the summation of forces? Summation of forces is equal to 0, so summation of forces in our Y direction. We have this A sub Y, there's our A sub Y right there. We have this negative 60, there's our negative 60 right there. And then we have the shear V sub B right here. So there's our shear force V sub B right there, and this is equal to 0. So we look at this, well, we've already solved previously in this problem for our A sub Y, and our A sub Y at the beginning when we solved this as a whole was 52 kilonewtons. So if that's 52 kilonewtons, we can plug that back in here for A sub y. So 52 kilonewtons minus this 60 kilonewtons minus V sub b is equal to 0. We can rearrange, solve this for V sub b. V sub b is our only unknown. It's our shear at B right there. So 52 kilonewtons minus 60 kilonewtons gives us a V sub b acting down right here in the negative y direction of negative 8 kilonewtons. So that now gives us our shear if we section it at B. So that's going to help us with our shear diagram. So now let's move on to the next one. So now what we're going to do is we're going to take a section here at C right there. So we'll come right down through our whole free body diagram right here, and we'll come right down through there. We'll section this off right there at C. So now what we have is now add in this 50 kilonewton force right there, this external load right there. So now we draw our free body diagram for this whole part here. Well, there's our A sub y right there from our support there. There's our external load of 60 kilonewtons from our distributed load up top right here. Here's our now external load right there, 50 kilonewtons right there. We're also going to have this shear V sub c right there and our M sub c there, which again, we're not concerned about at the moment right now. So let's take a look at summation of force in our y direction. It's equal to 0 for equilibrium. This is equal to, we have our A sub y, we have our negative 60, negative 50. So A sub y, negative 60, negative 50. And now we also have this negative VC right there that we'll plug in right there. This is all equal to 0 in equilibrium. Same standard XY coordinate system where y is positive up. We know our AY is 52 kilonewtons from the first part of the problem right there. We can plug that in right there. Our only unknown now is our VC. Plug in, we have 52 kilonewtons minus 60 kilonewtons minus now this 50 kilonewtons minus the V sub c is equal to 0. Let's move this V sub c over to this side, eliminate the negative. So we have 52 kilonewtons minus 60 kilonewtons minus 50 kilonewtons is equal to V sub c. Well, we can cancel this down right here. That's left with the 2 right there. So we'll end up with V sub c is equal to negative 58 kilonewtons. So this is now our shear force at C when we take our section right there. So now what we're going to do is go all the way right before our last support right there at D and take our section right there. So we'll come right down here, come right like this. So now we'll draw out our free body diagram here. So we have our A sub y over here, negative 60 kilonewtons, negative 50 kilonewtons right there. Then we have our shear V sub D right there, and we have our moment M sub C right there. So we can plug this in, summation of force in y direction, A sub y, where A sub y is 52 kilonewtons, so we can plug that in right there. Minus 60 kilonewtons, minus 50 kilonewtons right there, minus this V sub D that we're looking for there is equal to 0. So we can say 52 kilonewtons minus 60 kilonewtons minus 50 kilonewtons minus V sub D is equal to 0. Do this all out, solve for our V sub D. Our V sub D is going to be 58 kilonewtons. So now we can take the information we found from all those free body diagrams and our equilibrium equations there, plug it in on this graph over here, and we can say, okay, well, we know our V sub A here, we solved that to be 52 kilonewtons, and our V sub B we solved to be 8 kilonewtons there. And then if we took this section right before that load right there, right before C, we'd find that to be negative 8 kilonewtons, and right after C, we'd find that to be negative 58 kilonewtons right there. And if we did it right before our line of final support there, this is negative 58 there. So we could draw our line from negative 52 right down to negative 8, from negative 8 to negative 8 right before that 50 kilonewton loads. And when that's added right there, it goes from negative 58 to negative 58 right there. And that is our shear diagram that way. Now, there is an alternative way for us to find our shear diagram right here and draw this out. And that's to recognize this relationship right here that VB minus VA is equal to the negative area under our load curve. Where the negative area under our load curve right here is going to be negative 60 kilonewtons, because this is the area under our load curve right there, is that 60 kilonewtons right there going from A to B right there. So we can say, okay, well, if I know that V sub A is 52 kilonewtons right there, I can plug that in. VB minus 52 kilonewtons is equal to negative 60. So therefore our V sub B, if we solve that out, would need to be negative 8 kilonewtons. So we can do that right down here. So now from this section here, what we know is that our maximum bending moment is going to occur when our V is equal to 0. our shear force is equal to 0. So we want to find what is that location when our shear force is 0. Well, looking at our shear diagram, our shear force is 0 right here at this new point that we're going to call E right here. So now we can calculate this simply by plotting this out, and we know, okay, well, if this right here is at 52 and this right here down here at this is at -8 right there, we can back out and figure, okay, well, where is this going to cross our axis right here? This is going to cross our axis right here at a value of 2.6 meters. And we can get this by plotting this in MATLAB or Excel or any of those things and just taking a look at when this line right here crosses our x-axis. Because we know if we have this whole triangle right here, we can have this whole distance over here on our y-axis right here, that this is going to be a total of -8 plus 52 right there. So that's going to be a total of 60 right there. And then we know we're going out over here a total of 3 meters right there. So now we have a triangle right here where we can say a squared plus b squared is equal to c squared, and we can get the total length of this guy right there. And then we could go back down from this right here and back out our angle right there. And this is going to be the same angle as this right here. So then we still have the length over here of 52. If we look at the smaller triangle with that same angle right there. And from that we can do out some trig and back out this distance right here, which we then back out to be 2.6 meters. So this is just doing some simple trig based upon our dimensions over here like this. Or like I said, if you wanted to plot this in MATLAB or Excel, you could also do it that way and just see right where it crosses the x-axis and back it out of the plot right there. Either of those is fine. If you're doing it by hand, I would suggest doing this trig right there, just as we discussed. Now there is even another method that we could use to find that value for x right there, where this intersects our x-axis right there and our v is equal to 0, which is our max moment right there, and that's to use similar triangles. We recognize that these two are both similar triangles right there, and we can say that, well, our 60 over 3 is equal to our 52 over our x value right there. So 60 over 3 is equal to 52 over x. We can rearrange this and say cross multiply 60 times x is equal to 3 times 52. Solve this for our x is equal to 3 times 52 over 60, or x is equal to 2.6. So if now we know the dimension of that triangle there, and this is 52 over here on the height, and our base right here is 2.6, then the area inside of this right here is equal to 1/2 base times height, or 1/2 2.6 times 52. So our area right here is now going to be equal to 67.6. So going back over here, that's where we get that x is equal to 2.6 right there from those similar triangles, or the trig, or our graphing like we discussed before. And now we can see that our absolute value of our max moment right there, when our v is equal to 0, and that's the max bending moment, this is equal to the area under the shear curve from A to E, which is the area of that triangle we just calculated, 1/2 base times height. So 1/2 base times height is 1/2 of 2.6 times our 52 right there. So that's where we got that value right there for our max is equal to 67.6 kilonewtons. So now the last thing that we need to do for this problem, for sample problem 5.8 here, is determine that minimum acceptable beam section modulus right there. So now we can use this S-min relationship there. We saw again that previous equation right there, that this is equal to the absolute value of our max right there over the allowable stress, where they gave us the allowable stress in the problem statement of 168 megapascals. So we can take that max bending moment right there, the absolute value of that, so 67.6 kilonewton meters, all divided by 160 MPa. And this right here, when we do this out, is equal to 422.5 times 10 to the -6 meters cubed. Or we can put this down into millimeters cubed right there. And the reason we want to do that there is if we go back to that Appendix E in our book right there, and we want to choose out the best standard section that meets this criteria, we can take a look at all of these right here and see these different shapes from that different appendix in the Appendix E in the back of the book right there. And what we see is the closest one to this right here is our 474 right there. So this is going to be a 360 by 32.9 shape right there that's going to meet our criteria the best right there. So this is a great example of a design problem where they gave us this information here, had to calculate all of this from the given information in order to choose the best standard section right there, which we did from our Appendix E in the back of our book.